Hello. How much current is needed to plate 5 grams of copper on cathode from CuSO4 solution in 2 hours? Before we can calculate this, we need to know some formulas, and we'll be looking at Faraday's laws of electrolysis and how to apply them in solving problems. So let's look at the laws of electrolysis. Electrolysis comes in when we are dealing with reactions that are not spontaneous. So we are using electricity to make the reaction happen because it is not spontaneous. So the first law of electrolysis states that the mass of substance deposited or liberated at an electrode is directly proportional to the quantity of electricity passed through the electrolyte. So assuming this is our setup, our setup for the cell, and we know that in electrolysis, as the process is going on, as time goes on, as time goes on, the anode is going to decrease in mass and the cathode is going to increase in mass. As time goes on, the cathode is going to increase in mass. I decided not to use equations here for just a simple understanding. And because we are using electricity to make this reaction happen, Faraday is saying that the quantity of electricity that we put in this cell to make it happen, is directly proportional to the amount of masses that will be deposited at the cathode. So if we are using W as the mass of sample deposited at the cathode, then our W should be directly proportional to the charge. So the mass of substance deposited at the cathode is directly proportional to the amount of charges that is passed through the solution. So in this case, we have to derive some equations that we'll be using to solve problems in this video. And we need that our charge is equal to IT, current by time. So replacing charge by IT, we get our W to be directly proportional to IT. Because we want to remove the symbol for proportionality, and we have to introduce a constant, and that constant is going to be Z. So our W now is equal to ZIT. So our W equal Kate. Our Z here is a term, our Z here is a term that we need to look for. So our mass deposited equal Z. So our Z, what is our Z? Our Z is electrochemical equivalent. So Z is electrochemical equivalent. So now let's name this formula as formula 1. W equal Z. Then we name it as our equation 1. Mind you, W is the mass of the sample deposited at the cathode. And our expression for our Z equal equivalent weight over Faraday's equivalent weight over 1 Faraday. And the formula for equivalent weight, let me represent this by E. So our Z equal equivalent weight over F. And expression for equivalent weight equal molar mass over N factor. Our N here is N factor. So if we replace the value for equivalent weight here into this equation, this is what we are going to get. We get our Z to be equal to molar mass over NF. over n factor by Faraday. That is the Faraday's constant. So in all, we know our W to be equal to Z, and then our Z to be equal to molar mass over NF. I prefer putting subscript F here to differentiate this. This N factor here, we can simply say the number of electron, the number of charge on the metal ion. Now, notice this equation 1, and then let's drive another equation, which is equation 2. So we just have to substitute the value of Z into this equation. Then we are going to get our W to be equal to MIT over NF. You can decide to bring a subscript F, or you can just leave it, but don't forget that is the number of electron, charge on the metal. We are going to notice this equation 2. So these are our two equations that we've derived so far from the Faraday's first law of electrolysis, where M here is the molar mass of the element in concern, N here is the N factor. I prefer calling it N factor, yes, and or you can also call it the number of charge on the metal ion, and this is the Faraday's constant, our time current. For here, this is our electrochemical equivalent. We'll be needing these formulas. Now that we are done with Faraday's first law of electrolysis, let's look at his second law of electrolysis, Faraday's second law of electrolysis, because we'll be needing all the formulas to be doing our calculations. And it states that for two or more cells connected in series, then the weight deposited is directly proportional to the equivalent weight of substance. So if we have two or more cells connected in series, then the weight of substance here is referring to what will be deposited at the cathode as time goes on. The weight here, or we can also call it mass, is directly proportional to the equivalent weight of substance. And in this video, we also learn how to calculate equivalent weight. So let's drive a formula here. In this case, if you have A, B, and C cells connected in series, then the weight of A, the ratio of weight of A over its equivalent weight, it should be equal to the ratio, the weight of B and equivalent of B. It should be equal to weight of C over equivalent weight of C. This weight here, because in the equations we have M in the equations, that's why we normally prefer using W for simplification. And this weight here simply refers to the mass of the substance that will be deposited at the cathode. And this is the equivalent weight. And we will learn how to calculate equivalent weight. So adding these to our equations, we have three equations. So for equivalent weight, let's say, equal to the molar mass of that substance over its N factor. And the N factor depends on the substance, whether it is acid, whether it is an acid, a base, or just a salt. We will not be talking much about equivalent weight here, but we just calculate for our calculation's sake. I have a video on that, so you can also check it out. So let's name this to be equation 4. Then now we can go ahead and start solving problems. Now, how much current is needed to plate 5 grams of copper on cathode from copper sulfate solution in 2 hours? So this is an electroplating problem. One of the applications of electrolysis is electroplating, where we can decide, because we know in electrolysis, as time goes on, substances are deposited on the cathode. So we can decide and look for a particular cathode, and we want this kind of substance to be deposited on it. Then we make a setup for it. then it will be deposited on it, either for decoration or for protection against corrosion. So let's look at this problem. We are looking for current. How much current? But we've been given the mass, and it's the mass of what? Mass of copper. We've been given mass of copper to be 5 grams. So mass of copper, let me use weight W, mass of copper to be 5 grams. And time was given out to be 2 hours. But we have to convert our time into seconds. So 2 hours, we know that an hour equals 60 minutes. So 2 hours is going to give us 60 by 60 minutes. Then we know that 1 minute gives us 60 seconds. So we just multiply by 60. So this is going to give our time in seconds to be 7200 seconds. For the n factor that we are talking about, is in salt is the same as the charge carried by the cation. So for copper sulfate, if we break copper sulfate into its component ions, this is actually copper 2, then SO4 2 minus. So for salt, the n factor equal to the charge carried by the cation, not the anion, the cation. So our n factor here is 2. So our n equal 2. Our mass to be 5 grams, our time to be 7200 seconds, and then our n to be 2. What formula are we going to use? We are talking about mass here, time, and then n factor. Let's try recalling our formulas. If you check well, you could see that our formula meet NEF can help us solve this problem. And we are looking for current. So we can go ahead and make current the subject here. So this is the formula that we are going to use to calculate for our current. And we know W to be our mass, N to be our n factor, F to be Faraday's constant, and then M here to be a molar mass. Molar mass of what? We are talking about copper, so molar mass of copper. So the time given to us, 7200 seconds. So let's start solving. Molar mass for copper is going to give us 63.55 gram per mole. So now substituting our I equal our mass, which is 5 gram, multiplied by our current, multiplied by our n factor, which is 2, multiplied by Faraday's constant, which is 96500 kilo, divided by our molar mass, which is 63.55 gram per mole, multiplied by our time, which is 7200 seconds. So this is going to give us 2.1 ampere. A solution of copper sulfate is electrolyzed for 10 minutes with a current of 1.5 ampere. What is the mass? What is the mass? What is the mass of copper deposited at the cathode and the charge passed? So we are looking for the mass and charge passed. We have our current I to be 1.5 ampere and our time in minutes to be 10. Now converting this to seconds, we just multiply it by 60 seconds. And this is going to give us 600 seconds. We are looking for two things, the charge and the mass of copper. And we know that charge equal IT. So substituting the value of current and time, we are going to get 1.5 ampere multiplied by 600 seconds. And this is going to give us 900 kilo. Now that we know our charge, we can go ahead and calculate for our mass. Mass equal meet NEF. The molar mass for copper still holds to be 63.55 gram per mole. And then our current is 1.5. We know our time. And then our n factor Looking at copper sulfate, when we break it into its constituent ions, you see the charge on copper is +2. So N factor for copper is 2. So we know our N to be 2. For Faraday's constant, we know it to be 96500 coulomb. So we can just go ahead and make substitution. So we know our W to be equal to molar mass, which is 63.55 gram per mole, multiplied by current, which is 1.5 ampere, multiplied by current and multiplied by our time, which is 600 seconds, all divided by NF. Our N factor is 2 by Faraday's constant 96550 coulomb. Punching this on your calculator will give us 0.2961 grams of copper. What mass of nickel metal can be plated on the cathode from a nickel sulfate solution using a current of 8 ampere for 50 minutes? Now we are looking for a mass of copper that, mass of nickel that can be plated on the cathode. We know our current, let me change our current to be 8 ampere and our time to be 15 minutes. And we have to convert this to to seconds. So we just multiply it by 60 seconds. And this is going to give us 900 seconds. We can get our N when we are looking at nickel sulfate. If we break this into ions, we are going to get 2 plus SO4 2 minus. So our N is 2. So our N is 2. Molar mass for nickel equal 58.69 gram per mole. So now for Faraday's constant, we know it already to be 96500 seconds. But then what formula are we going to use? As far as we are dealing with mass, looking at the parameters, this formula right here will help. Meet NEF. So we know our molar mass to be 58.69 gram per mole. 0.69 gram per mole multiplied by our current, which is 8 ampere, multiplied by time, which is 900 seconds, all divided by our N factor and then Faraday's constant. Our N here is 2, so 2 by Faraday's constant 96500 coulomb. So this is going to give us 2.1895 grams of nickel that we need. Find the time required to deposit 1.92 gram of copper from copper sulfate solution by passing a current of 1.5 ampere. Molar mass for copper is given to be 64. So let's go quick and write our parameters. Our mass, like I've been using W for mass here, equal 1.92 grams, and then our current equal 1.5 ampere. Molar mass for copper given here is 64 gram per mole. And what are we to calculate? We are to find the time required. So we are to look at an expression that relates time in these quantities. Always our W equal meet NEF. So we are looking for time. So we just make time the subject. This is going to give us MNF, over MI. This is W. That is why I prefer using W for mass. So substituting our values in, we have our weight to be 1.92 and our N factor What is our N factor here? Copper sulfate, if we break them into ions, this is going to be 2 plus and 2 minus. So our N is 2. So multiply by 2, multiply by Faraday's constant, which is 96500 kilogram, divided by molar mass for copper, 64 gram per mole, multiplied by current given, which is 1.5 ampere. So this is going to give us 386, 60 seconds. Sometimes you may be required to convert your time into minutes when it is given to you in minutes. Your final solution, you can convert it into minutes. We are going to speed on this one. 0.1978 of copper is deposited by a current of 0.2 ampere in 50 minutes. What is the electrochemical equivalent of copper? And here we are looking at the electrochemical equivalent of copper. So we have mass of copper to be 0.1978 grams. Then we also have our current to be 0.2 ampere and our time in minutes to be 50. Converting this to seconds, we just multiply it by 60, and this is going to give us 300 seconds. So what relation can we use to get electrochemical equivalent? From our first derived equation, we know that our weight equals electrochemical equivalent by current by time. So this formula is what we are going to use. This relates our electrochemical equivalents. So we know our W to be equal to Z, and we want our electrochemical equivalent. We just make that the subject and go ahead and substitute the values in. So this is going to give us, we know our mass already to be 0.1978 grams, all on 0.2 our current, 0.2 multiplied by our time, 300 seconds. So this will be giving us, if you point this on your calculator, this will be giving us something like 0.003296 seconds. No. So this is the value for our electrochemical equivalent. Now, I don't want this video to be lengthy, so I might decide to solve some of these examples in the next video. Then if so, I'll leave a link in the description section below, or you'll be notified before the end of the video that there's another one you can watch and for much better understanding. It's going to add up to what we've learned so far.